Title: Fundamentals of Algorithms, the Logic of Problem Solving. Today, we are going to explore one of the most fundamental concepts in computer science: algorithms. Every application that we use today, whether it is Google Search, ChatGPT, Amazon recommendations, online banking, or autonomous vehicles, is powered by algorithms working behind the scenes. An algorithm is much more than just computer code. It represents a structured way of thinking and solving problems. Before programmers write software in languages such as Python, Java, or C++, they first develop an algorithm that describes exactly how the problem should be solved. Throughout this presentation, we will understand what algorithms are, why they are important, how they are designed, and how their efficiency is evaluated. We will also look at classic examples, common problem-solving strategies, and performance analysis. By the end of this session, you should have a strong understanding of algorithmic thinking and appreciate why algorithms are considered the foundation of all computing systems. Title: What is an algorithm? Let us begin with the definition of an algorithm. An algorithm is a finite, well-defined, and unambiguous sequence of instructions designed to solve a particular problem. Every algorithm begins with one or more inputs, processes those inputs through a series of logical steps, and finally produces an expected output. There are three important characteristics that every algorithm must satisfy. First is input and output. Every algorithm accepts input data and produces meaningful output. Second is precision. Each instruction must be clear and leave no room for interpretation. If an instruction is ambiguous, different people or computers might execute it differently, leading to inconsistent results. Third is finiteness. Every algorithm must eventually stop. It cannot continue forever. After a finite number of steps, it should produce the desired solution. The term algorithm itself originates from the Persian mathematician Al-Khwarizmi, whose mathematical procedures formed the basis for systematic computation. His contributions were so influential that his name evolved into the modern word algorithm. In summary, algorithms provide the logical blueprint for solving problems efficiently and systematically. Title: Computational Thinking, the Core Pillars. Every algorithm, regardless of its complexity, is built upon three fundamental control structures. The first is sequence. Sequence means instructions are executed one after another in a specific order. For example, when making tea, we first boil water, then add tea leaves, then pour the tea into a cup. Changing the order would not produce the desired result. The second structure is decision, also known as conditional logic. Here, the algorithm chooses different paths depending on whether a condition is true or false. For example, if the user's password is correct, access is granted, otherwise, access is denied. The third structure is repetition, commonly implemented using loops. Instead of writing the same instruction multiple times, we repeat it until a condition is satisfied. For instance, calculating the average marks of 100 students involves repeating the same calculation for every student. Almost every computer program combines these three building blocks, sequence, decision, and repetition, to create complex applications. Title: Why algorithms matter. Now let us understand why algorithms are so important. Algorithms are considered the foundation of computer science because every software system depends on them. Search engines use sophisticated search algorithms, social media platforms use recommendation algorithms, and artificial intelligence systems rely on learning algorithms. Interestingly, A single problem can often be solved using multiple algorithms. For example, searching for a name in a list can be performed using linear search or binary search. Both solve the same problem but differ significantly in speed and efficiency. Another important advantage of algorithms is abstraction. Algorithms focus on logical steps rather than programming language syntax. Once we design a good algorithm, it can be implemented in Python, Java, C++, or any other programming language. Therefore, algorithms encourage systematic thinking and make software development more organized and efficient. Title: Euclid's Greatest Common Divisor Algorithm. This slide introduces one of the oldest and most elegant algorithms in mathematics, Euclid's algorithm for finding the greatest common divisor, or GCD. Suppose we want to find the largest number that divides two integers without leaving a remainder. Euclid's method works by repeatedly dividing the larger number by the smaller number and replacing the larger number with the smaller one while replacing the smaller number with the remainder. This process continues until the remainder becomes 0. At that point, the current divisor is the greatest common divisor. For example, to find the GCD of 48 and 18. 48 divided by 18 leaves remainder 12. 18 divided by 12 leaves remainder 6. 12 divided by 6 leaves remainder 0. Therefore, the GCD is 6. This algorithm is remarkable because it solves the problem very efficiently using only a few simple operations. Title: Describing algorithms. There are several ways to represent algorithms. The first is natural language. Here, the algorithm is written using ordinary English. This approach is easy to understand but can sometimes be ambiguous because different readers may interpret the instructions differently. The second method is flowcharts. Flowcharts represent algorithms visually using standardized symbols such as rectangles for processes, diamonds for decisions, and arrows indicating the direction of execution. Flowcharts are particularly useful when explaining algorithms to beginners or non-programmers. The third method is pseudocode, which is the most widely used approach in software development. Pseudocode resembles programming code but avoids language-specific syntax. It focuses entirely on the logical sequence of operations. Among these methods, pseudocode offers the best balance between readability and precision, making it the preferred choice for algorithm design. Title: Common Algorithmic Paradigms. Designing algorithms is not just about writing instructions. It also involves selecting an appropriate problem-solving strategy, known as an algorithmic paradigm. Some of the most common paradigms include brute force, where every possible solution is tested; divide and conquer, where a problem is divided into smaller subproblems, solved independently, and then combined. Merge sort is a classic example. Greedy algorithms make the best local decision at each step with the hope of achieving a globally optimal solution. Kruskal's algorithm is one example. Dynamic programming solves complex problems by storing previously computed solutions to avoid redundant calculations. Backtracking systematically explores possible solutions and abandons paths that cannot lead to success. There is no universally best paradigm. The choice depends entirely on the characteristics of the problem being solved. Title: Searching and Sorting. Searching and sorting are among the most fundamental operations in computer science. Searching involves locating a particular element within a collection of data. The simplest searching technique is linear search, where each element is examined one by one until the target is found. A much faster method is binary search, but it only works if the data is already sorted. Binary search repeatedly divides the search space in half, dramatically reducing the number of comparisons. Sorting involves arranging data in a meaningful order, such as ascending or descending. Basic sorting algorithms include bubble sort and selection sort, which are simple to understand but inefficient for large datasets. Modern systems often use advanced algorithms such as quick sort, merge sort, or heap sort because they perform much better with large amounts of data. Efficient searching and sorting are essential in databases, search engines, operating systems, and artificial intelligence. Title: Efficiency and Complexity. Having a correct algorithm is not enough, it must also be efficient. Algorithm efficiency is commonly analyzed using Big O notation, which describes how an algorithm's running time grows as the input size increases. An algorithm with O(1) complexity executes in constant time, regardless of the amount of data. An O(log n) algorithm grows very slowly with increasing input size. Binary search is a classic example and is considered highly efficient. An O(n superscript 2) algorithm, such as bubble sort, becomes much slower as the dataset grows because of nested loops. Understanding computational complexity helps software engineers choose algorithms that scale efficiently for real-world applications involving millions or even billions of records. This is why performance analysis is an essential part of algorithm design. Title: Mastering the Toolkit. In conclusion, algorithms provide the logical foundation for all software systems. Whenever we encounter a problem, we should first clearly define the inputs, outputs, and constraints. Next, we should select the most suitable algorithmic paradigm based on the characteristics of the problem. Finally, we should think in logical steps, verify the correctness of the algorithm, and continuously improve its efficiency through testing and optimization. Remember that programming languages change over time, but algorithmic thinking remains timeless. Strong problem-solving skills and a solid understanding of algorithms are essential for careers in software engineering, artificial intelligence, cybersecurity, data science, and many other computing disciplines. Thank you for your attention. I would be happy to answer any questions.